Biocementation is an innovative field of study where we draw inspiration from nature to understand how soil particles are naturally strengthened and cemented together. Our objective is to develop sustainable alternatives to traditional Portland cement and chemical binders, which can pose environmental concerns. In nature, we see that certain bioagents induce precipitation of minerals such as carbonate minerals in soil pores. This leads to the binding of soil particles together, creating a stronger and more stable soil structure. Biocementation has the potential to offer a sustainable and eco-friendly solution for geotechnical and geo-environmental problems that result from the lack of strength in soil. One of the advantages of biocementation is that it is inspired by nature. Because it is believed that nature, with 3.8 billion years of experience, has perfected a system whereby all of its processes are efficient, cost-effective, and reliable. One of the applications of biocementation is for earthquake liquefaction mitigation. Earthquake liquefaction occurs when soil, saturated with water, loses its strength and stiffness during an earthquake, leading to a loss of bearing capacity and increased settlement of buildings and infrastructure. This can result in significant damage to buildings and infrastructure, leading to the loss of lives and financial losses. For earthquake liquefaction mitigation, the biocementation solution can be injected into the soil, where it reacts with the soil particles and binds them together, creating a stronger and more stable soil structure. The near-water viscosity of the biocementation solution makes it possible to apply the solution under existing structures without disrupting them. Dust control is another application of biocementation. In arid and semi-arid regions such as Arizona, dust can pose a significant problem, as well as in industries such as mining and construction. The conventional method for dust control involves the use of water trucks, which may require several hours of spraying a day. However, biocementation can save a substantial amount of water. By spraying the biocementation solution on surfaces such as mining sites or roads, the dust particles are bound together, creating a crust. This crust provides a stable surface that significantly reduces dust emissions, thereby reducing the need for frequent water spraying. Biocementation contributes to better air quality, reduces health risks associated with dust exposure, and improves food safety by preventing dust contamination of crops. Moreover, biocementation can enhance traffic safety by improving visibility on roads. Nature provides us with various mechanisms for biocementation, and one of the most extensively studied methods is urea hydrolysis. In this process, urea acts as the primary substrate and is hydrolyzed by the urease enzyme to generate carbonate and alkalinity. The presence of calcium ions allows the carbonate to combine with them and form calcium carbonate, which is a natural cementation agent. Urease plays a crucial role as a catalyst, accelerating the reaction rate by 10 power 14 times. Urease can be obtained from ureolytic microorganisms or extracted from urease-rich plants like jack beans. When microbes are used for biocementation, it is known as microbially induced carbonate precipitation, MICP, and when the plant-extracted urease enzymes are used, it is called enzymatically induced carbonate precipitation, EICP. On this slide, we present the results of the EICP treatment on the soil specimen. In the middle, you can see a before and after comparison of the soil after the treatment. On the left, we show how we measure the strength of the treated specimen using the unconfined compression test. This test applies compression force on the specimen until it fails. Our observations reveal that EICP treatment can lead to an unconfined compression strength of up to approximately 2 megapascals after a single treatment cycle. This slide showcases 3 different applications of EICP at large scale. On the left, you can see the EICP-treated slope surface, which has been stabilized against wave erosion. In the middle, the EICP solution is sprayed on the surface to form a crust for dust control. On the right, biocemented columns have been created using EICP technology. Although EICP has shown promising results in soil stabilization, there are still research questions that require further fundamental and microscale understanding of the process. One of the main questions is why EICP improves the strength of different soils differently. To address this, our team is conducting microscale studies using advanced identification tools such as scanning electron microscopy, X-ray diffraction, Raman spectroscopy, Fourier transform infrared spectroscopy, and others. These tools allow us to observe and analyze the mechanisms of calcium carbonate precipitation and its attachment to soil particle surfaces, which will provide insights into the variations in strength improvement across different soil types. By gaining a deeper understanding of these microscale processes, we can optimize the ICP treatment for a wider range of soil types and applications. Thank you for your attention. Please reach out to us if you have any questions.